So now we're ready to address a profoundly important question, and that is, how is energy released from a chemical reaction actually measured? And what I'm going to describe here is what's called affectionately a bomb calorimeter. And this device has been used by thousands of people across the globe to measure the chemical release from a reaction. And the way a bomb calorimeter works is that we have a reaction vessel within which the reaction takes place. And we're going to look at the case where we test the energy release from gasoline. So gasoline is C8H18, and we're going to react that with oxygen, and when we do that, the product is CO2 and water. But we have to balance that chemical reaction, and we do that. We can do that very quickly to balance the hydrogen and oxygen on the left-hand side and the right-hand side. So now we're combusting gasoline inside this little vessel. And we can initiate that chemical reaction with an electrical spark, which is exactly how gasoline is ignited in your automobile engine. And when we ignite that gasoline, if we did not contain it within a very strong vessel, which is what this is, it would in fact explode, blow up, and destroy everything around it. But we lock down that volume within which that gasoline is ignited, and we prevent the volume from changing at all. So this term bomb calorimeter is an affectionate term because actually nothing explodes outside of that containment vessel. It's locked down because the volume is fixed. Now, the system is then that chemical reaction. The surroundings are everything else you see in the diagram. The water that's in this container, we have a motorized stirring element, a thermometer, we've got a steel container that is surrounding the system, which is the chemical reaction. So the surrounding is everything else other than that chemical reaction. So the first law of thermodynamics then says the change in the internal energy of that system is equal to Q plus W. We always know that's the case. And that begins to stabilize our thinking, because when we look at this system, we recognize that there is certainly heat coming out generated by the combustion of gasoline. So we know what the heat is. We also know what the form of the work term is. It's a force times a distance. But if we've locked down that combusted system so that the volume cannot change, it means there's no displacement. The product of force times a distance has to be zero. In fact, when you detonate a chemical reaction like this, you can't hear anything because the walls of that container don't deflect, and there's no sound connection between the chemical reaction and the outside. But we know something else. We've fixed the volume, so we know what the heat term is. That's the heat released at constant volume. And this was used for decades to measure the heat release of a chemical reaction. And it was done because the heat release, Q sub V, which was the change in internal energy, was simply equal to the proportionality constant times the change in temperature. And the proportionality constant was the heat capacity of the surroundings. This is exactly the same technique that Joule used to convert mechanical energy to heat. And it's a very simple way of measuring it, because if you simply measure the change in temperature, you can do the thermometer measurement before and after the reaction is done and determine exactly how much energy is released, because heat capacity is measured in kilojoules per degree Celsius, and temperature is measured in degrees Celsius, and so the result is in kilojoules. And because heat is energy, that's exactly the right unit that expresses the energy released from the chemical reaction.